Okay, February, March 2024, paper 6. Question 1. We have a ruler, and the student is trying to determine the mass of the ruler by a balancing method. Now he places a circular load on the meter ruler as shown. We need to determine the distance d of the center of the load. We need to find the center of this load. How can we find the center of this load? Very simply, we just find the reading before and after and take the average of these readings. The initial reading was 26.5 and the final reading was 29.5. Finding the average would be 29.5 plus 26.5 divided by 2. This would give a reading of 28 centimeters. Okay, now the student adjusts the position of the meter ruler on the pivot until the meter ruler is as near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. What is the technique? What should he do? He simply should move the ruler slowly. Okay, he needs to move the ruler slowly to the left and right, to the left and right. He needs to move it to the left and right until it tips over to either side. Okay, until it tips over to either side. It will be balanced by then. Student finds that the ruler is as near as possible to being balanced when the pivot is at 47.6, the 47.6 centimeter mark. Calculate the distance A of the center of the load from the 50 centimeter mark. Okay, that's easy. 50 minus D, 50 minus 28 is 22 centimeters. Calculate the distance B of the center of the load. Okay, you can use the equation, the position of the pivot minus D. The position of the pivot was 47.6 minus 28. This would give a value of 19.4 centimeters. Okay, quite easy. Now we have a table. Definitely, we will need to plot a graph. Okay, plot the graph. A on the y-axis and B on the x-axis. You do not need to start from the origin. Okay, quite easy. A slash centimeters on the y-axis and B slash centimeters also on the x-axis. We will not start from the origin. Okay, A, it's quite easy. We can scale it 20, 25, 30, 35. Okay, 25, 30, 35, 40, and 45. Quite easy. What about B? 45, 40.5, 35, 22.5. So probably we will need to start from 20. Okay, moving up by fives, 25, 30, 35. Yeah, okay, this is good. 40 and last but not least, 45. We can remove a B slash centimeters. Okay, 45, B slash centimeters. Okay, this would be quite an easy graph. Okay, take note that each two small squares, okay, every two small squares are worth 1 on either axis, on the x-axis and on the y-axis. Okay, okay, two squares. So basically, each square is worth half point. Okay, we can start 45 on the y-axis and 40.5. So 40.5 and 45. 40.5 and 45 would be exactly here. Okay. 35.2 and 40. 35.2 and 40. Okay. 31.5 and 35. 31.5, 3 squares after 30 and 35. Okay, that's easy. 26 and 30, also easy. 26 and 30. Last but not least, 22.5 and 25. 22.5 would be exactly here with the 25. Again, while plotting, we have to put small x's, okay? Preferably small x's or dots with circles. Draw a straight line. Okay, we need to draw a straight line, and probably we need to find the gradient, yes. How to draw the straight line? This would be an easy straight line, actually. Um, okay, using this, we can draw a straight line, which would go, yeah, to be something like this. Yeah, this is a straight line. We have 2 points above the line, we have 2 points below the line, and this is what we call a line of best fit. How can I find the gradient? Now, to find the gradient, we will need to use the triangle method. Triangle method, simply we need to draw a triangle. We need to complete the triangle using the two furthest points apart. Usually we have to use the two furthest points apart. Again, you can use two other points. For example, the second point with the fifth point. It would be okay, but never, ever use two very close points. For example, don't use the second and third point. Don't use the third and fourth point. Okay, never use two very close points. These points have to cover at least 70 or 80% of the graph. Okay, so preferably we use the two furthest points apart. Again, I drew the triangle method, and I can use the equation y2 minus y1 over x2 minus x1, which is basically the rise over run. In this case, 45 minus 25 over 40.5 over 22.5. Okay, that's quite easy. Okay. Mhm. Yeah. 45 minus 25 over 40.5 minus 22.5. This would give a final answer of, let's calculate it quite quickly, okay, 1.13, okay, 1.13. Okay. Calculate the mass m of the meter ruler using the equation m equals k over g minus 1, where k is 25 grams. Okay, 25 over g, which was 1.13 minus 1. Can use the calculator. This would give me a mass of 188. Again, given appropriate unit for the mass, an appropriate unit would definitely be grams. Definitely. You can never use kilograms. 188 kilograms for 1 meter ruler. That's illogical. Definitely illogical. Okay. The accuracy of the result obtained by this procedure depends on the meter ruler without a load. Balancing with the pivot at 50 centimeter mark. Okay, at the 50 centimeter mark. As finds that this does not happen, she adds a small piece of modeling clay to she adds a piece of modeling clay to one end of the meter ruler to correct it. Suggest if this is a suitable change for this experiment and explain your answer. Again, this experiment, what did we do in this experiment? Why were we initially conducting this experiment? The student determines the what? The mass of the meter ruler. So in this experiment, she actually wants to find out the mass of the meter ruler. And by finding the mass of the meter ruler, she ends up adding a small piece of modeling clay on one end of the meter ruler. Would this give an accurate result? Definitely not. Definitely not. Suggests that this is a suitable change? No. Why? Because she changed, okay, the total mass, the total mass of the ruler, which would definitely give inaccurate results for the mass of the ruler. Okay, moving on. Question 2, we have a circuit, we have a meter, some resistors in series. Now on figure 2.1, draw a voltmeter connected to measure the potential difference. Quite easy. Voltmeter in parallel above or below the resistors. You can draw it above or you can draw it below the resistors. Now I have a voltmeter and an ammeter. I need to take the readings, okay, and record them in the table. The reading of the voltmeter is 3.1. The reading of the ammeter is, this is 0.1, okay? So 0.12, 0.12. definitely later on he will ask me to complete the table headings, so I'll just go on and complete them right now. V would be in volts, I would be in amperes, and R would be in ohms. Okay, and most probably he will tell me to calculate the resistance. Okay, yeah, here. Calculate and record the resistance and then complete the column headings, which is okay. How can I calculate the resistance? R equals V over I for each of them. Okay, I can just write them down quite quickly. 3.1 over 0.12, 2.9 over 0.22, and 2.6 over 0.86. Okay, let me calculate them quite quickly right now. The first one would be 25.8 ohms. The second one would be 13.2 ohms, and the last one would be 3.02 ohms. Okay, good. Circuit B and circuit C. Again, circuit B, we had one resistor and two of them were in parallel. Circuit C, the three of them were in parallel. Calculate a resistance RA. Use the values R from circuit A and the equation. RA equals R over 3, okay? The resistance of RA, which was 25.8. 25.8 divided by 3. 25.8 divided by 3. This would give me a total resistance of 8.60 ohms. Okay, three significant figures. Okay, the other one would be R over 1.5. Okay, which was again 13.2 over 1.5, and last one, this is 13.2 over 1.5, and the last one is 3 times 3.02. This would give me a total resistance of 8.80 ohms. RC would be 9.06 ohms. RA, RB, and RC. A student suggests that RA, RB, and RC should all be equal. Are they equal? 8.60, 8.80, 9.06. They definitely seem to be quite close. And they are equal. Yes, we will consider them to be equal. You can calculate it. Definitely, you can calculate it. For example, 9.06 divided by 8.80 or 9.06 divided by 8.60, or you can just calculate 8.80 over 8.60. All of these numbers would give you a difference, a percentage error, which is less than 10%. So if you have a percentage error less than 10%, this means that you are that the numbers are equal. Okay, so the statement, what should I write down in the statement? Students suggest that they are equal. Yes, I do agree. Yes, agree. Why do I agree? Justification, because the numbers 9.06, 8.80, 8.60 are all close. And they definitely are within, okay? And within the limits of experimental accuracy. The limits of experimental accuracy. Okay. Less than 10%, okay? Less than 10% error. Okay. Student investigates the resistors in circuit A using a variable resistor to change the current. Uh, Draw the symbol for a variable resistor. Okay, this is a variable resistor. Suggest one advantage of using a variable resistor. Why would using a variable resistor be an advantage? Okay, why is it an advantage? Because it can change the current to specific values. It can change, okay, the current to specific values. Okay, it's quite easy. Question 3, we have a converging lens, an object and a screen. The student sets up the apparatus as shown. Suggest one precaution that must be taken when setting up the apparatus. Again, one of the most famous precautions while dealing with an illuminated object, a lens, and a screen is to make sure that they are all perpendicular to the surface. Okay, the object, lens, and screen must be perpendicular to the surface. Okay, perpendicular to, okay, the surface. You can also say that they must all be on the same horizontal surface. The student sets the distance u between the object and the lens to 20 centimeters. He places the screen near the lens and moves the screen until a sharp image of the illuminated object is on the screen. Describe a technique for obtaining an image that is as sharp as possible. How can I find a sharp image on the screen? Very simply, what should I do? I should just move the screen. Okay. All you need to do is what? Move the screen slowly to the left and to the right. Okay. Move the screen slowly to the left and right until a sharp image appears. Sharp image, okay, appears. Quite easy. Measure V1, the distance from the lens to the screen. Measure the distance V1 using your ruler. Using your ruler, the distance would be 8 centimeters. If the figure is drawn 1/10 the scale, this means that I need to multiply V1 times 10. If it was 1/5 the scale, for example, I would have multiplied by 5. So 8 times 10 is 80 centimeters. The shapes of the illuminated object and the image are shown in full size. Measure H0, 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 whatever, and H1. Again, using the ruler, we can measure these distances. H0 would be 1.2. HI would be 4.8. Calculate the value M for the magnification HI. Okay, 4.8 over 1.2. This is 4. So the magnification M is 4 right now. Calculate the value. Or calculate the value F1 for the focal length using the numbers V1 over M plus 1. V1 was 80. Capital V1, not small V1. Okay, capital V1 is 80 over 4 plus 1. 80 over 4 plus 1 would give a focal length of 16 centimeters. Again, this is a focal length, so you need to write down the unit, okay? Whenever I use a focal length, usually the unit is in centimeters. The magnification does not have a unit. Magnification does not have a unit. Why? Because it's a ratio. This is a ratio. Therefore, there is no unit for the ratio. Describe one difficulty that is experienced when using a ruler to measure the height of the image in this experiment. One difficulty. Okay. What could be one difficulty that is experienced while measuring the height of the image? Okay, of the image, again, of the image. The problem is if we look at the apparatus setup, this is the image that should appear. The image should appear somewhere here. And then you will use the ruler, okay? I'll put the ruler like this and measure the height of the image. While measuring the height of the image, what will happen? My hand and the ruler will come in front of the image. So basically, the image will kind of disappear behind the hand. The image will disappear behind the ruler. Okay, why? Because the ruler and the hand are in front of the image. They get in the way of the image. So the hand and the ruler hmm, get in the way of the image. Okay, what is one improvement that I could do? Very simply, I can use a translucent Okay, translucent screen, and measure the height and measure the height from the other side. Measure the height from the other side. The student adjusts position of the lens so that now he will increase the distance between the object and the lens. U will now become 40 centimeters. Calculate the second value for F2 using the equation U times V2. So 40 times 25.1 divided by 40 plus 25.1. This will give me a focal length of 15.4 centimeters. Suggest which value of focal length F1 or F2 might be more accurate and explain your answer. F1 or F2, which of them is more accurate? F1, we calculated it when U was 20 centimeters. F2, we calculated it when U was 40 centimeters. The problem is, whenever you increase the distance between the object and the lens, what happens to the image? The image gets smaller. Whenever you increase the distance between the object and the lens, the image gets smaller. So in this case, which would be more accurate? Actually, F1 would be more accurate. Why is F1 more accurate? Because the image is now larger. The image in the first case would be larger. Why is that better? Because this would decrease the inaccuracy. Okay, as you increase the distance, the image decreases, the height of the image decreases, and the inaccuracy increases. Okay, we can say it in other words. Okay, F1 is more accurate, is more accurate. Why is F1 more accurate? Because as U decreases, what happens? The image height, okay? The image height increases, okay? And when the image height increases, this is more accurate and becomes more accurate and is more accurate to measure. Okay? More accurate to measure. Good. Planning an experiment. A student investigates the effect of insulation on the cooling of a liquid. Plan an experiment which will enable her to investigate how changing what? Changing the thickness of insulation surrounding a beaker affects what? Affects the rate of cooling. Thickness of the insulating material. How does this affect the rate of cooling of hot water? Okay, this is quite simple, quite easy. What should we do? What should we do? What's the independent variable for this question? The independent variable for the question is the thickness of the insulation. So very simply, I will write down the range of values, which are the range of values, my independent variables, okay? My independent variable, what is the thickness, okay? The thickness of the insulation. And I'll write down 5 different thicknesses, such as 5 millimeters, 10 millimeters, 15 millimeters, 20, okay, and 25 millimeters. Again, you have to use a suitable unit. You cannot write down 5, 10, 15, 20 centimeters and definitely not meters, but centimeters would be too thick for an insulation. 5 millimeters, 10 millimeters, 15, okay, that's quite suitable for the thickness of an insulating material. These are the range of values that I will be using. The apparatuses available are a glass beaker, supply of hot water, okay, a lid, and some strips of insulation. List any additional apparatuses. The method, state the key variables. What are the key variables in this question? I need to measure the rate of cooling. We have so many key variables. We can write as much as we can think of. What are the controlled variables? Okay, controlled variables in this equation, in this question would be definitely the volume of water. Okay, the volume of water, the initial temperature of the water, the room temperature. Okay, you can say the material of the beaker, material of the beaker, and the material of the insulation, which is very important, material of the insulation. And last but not least, you can either say the final temperature or the time taken. You cannot say both. You cannot say both because they will be different. Okay, one of them will differ. So, for example, I will say the time taken. Okay, the time taken for the experiment. Okay, for example, I will set the time for each experiment to be 2 or 3 minutes. Okay, why? Because by the end of each of these experiments, you will have a different final temperature for each of these insulations, and that's how we will calculate the rate of cooling for each of them. Okay, these are some of the controlled variables that you will be using. What are the additional apparatuses I need? Apparatuses. What are the different apparatuses that I will be needing? For example, I definitely need a stopwatch. You will most likely need a thermometer, probably a measuring cylinder. Okay. He already told you that you have a supply of hot water, so you do not need a Bunsen burner. Okay, because you already have a supply of hot water. If you had a supply of cold water, then you most probably would have needed some sort of heater or a Bunsen burner. What is the method? It's a very simple method. Okay, what is the method that I will be conducting? First of all, add the same volume of water. Add the same volume of water to the beaker. Measure, okay, the initial temperature. Measure the initial temperature of the water. Um, add the insulation. Okay, add the insulating material. Leave the water for a constant amount of time. Okay, leave the water for a fixed amount of time. Fixed amount of time, and then measure the final temperature. Measure the final temperature. And then to measure or to calculate the rate of cooling, how can I calculate the rate of cooling? Calculate, okay, the rate of cooling. How can I calculate the rate of cooling? We know the equation. Initial temperature minus final temperature. Initial temperature minus final temperature over the time taken. Over the time taken. And then we have to say that we must repeat the procedure for all the different thicknesses of the insulation. Okay, repeat the procedure for all different thicknesses available. Repeat the procedure. Okay, so now I'm done with the apparatuses, the method. He needs me to draw a table. Okay, I can draw the table here. Again, you may draw a diagram. You do not have to draw the diagram. You're not required to draw the diagram. I can draw the table in this space provided. The table would have uh, quite some columns. First column would be the thickness of the hmm, thickness of the insulation in millimeters. The initial temperature in degrees Celsius. The final temperature also in degrees Celsius. The time taken in seconds. And you can write down the rate, which would be in degrees Celsius per second. Degrees Celsius per second. Thickness, initial temperature, final temperature, time taken, and rate of cooling, which would be in degrees Celsius per second. Last but not least, I need to write down a conclusion. How will I reach a conclusion? Okay, very simply, what will I do? Conclusion. Some very systematic steps. What are the steps in the conclusion? For each thickness, repeat the experiment. Okay, repeat the experiment more than once. Okay, more than once, and take average. And take average. Record the readings in the table. Record the readings in the table. And then finally, after you record the readings in the table, you need to compare the results. Compare the results of the cooling rates. Okay, this is quite an easy experiment to conduct. Okay, that's it.